Okay, so hi everyone, welcome back. So our next speaker is Kayo, and Kayo currently is a research intern at DeepMind, working with Chris Dyer in the language team, and she's starting her PhD at the UC Berkeley with Dan and Jakob Sohn, and she works on model interpretability, context-aware machine translation, and sign languages. So she has published several very impressive papers in the top-tier conferences. And today, her talk's title is Understanding, Improving, and Evaluating Context Usage in Context-Aware Translation. So now the floor is yours.
Thank you very much for the introduction. Let me try sharing my screen. Okay, does everything work as it's supposed to?
Yes. No.
Okay, great.
Wait a second.
Wait, sorry. Yeah.
Okay. Yeah.
Okay.
Now it
great.
works.
Hi everyone. My name is Kayo. Thank you very much for inviting me to this great workshop. And today I will talk a little bit about current efforts to understand, improve, and evaluate context usage in context-aware machine translation. And the works that I'm going to talk about today were done while I was a master's student at Carnegie Mellon University with my colleagues Patrick, Danish, Aditi, and my supervisors Andre and Bram Ubig. I prepared a brief slide to introduce myself, but Gongbo already did a better job than I could have done myself to introduce myself, so I can skip that. Okay, so to start off the talk, why do we need context-aware translation? Well, let's take a look at this example. Here, what does the word mole refer to? Well, if the previous sentence was, things could start to get dangerous if the ministers find out, then mole probably refers to a spy. But if the previous sentence was, could it be anything serious, doctor? Instead, the mole refers to a birthmark. So depending on the context, the meaning of the word changes, and therefore the translation depends on the context as well. Current neural machine translation models are reasonably good at sentence-level translation for high-resource language pairs, such as English and French. So for example, here a popular provider correctly translates the sentence that we give. However, when the context changes, the correct translation should now be c'est quand de beauté, but the model does not pick up on the changing meaning. Current models often fail to produce adequate translations on a document level when there are ambiguous words that requires additional context to resolve. Another example is for the translation of the neutral English pronoun they, where since they refers to implications, which is a feminine noun in French, the pronoun should be the feminine elle instead of the masculine il. To address the difficulties in document-level translation and the importance of context, several methods over the last 4 or 5 years have been proposed to incorporate context in neural machine translation. And this includes feeding the contextual sentences to standard NMT models by concatenating them to the input, or using different encoders for the context, or as well as using cache-based memories or models with hierarchical attention mechanisms for the context. But even with the necessary context, these models perform poorly on translating relatively simple discourse phenomena, such as anaphoric pronouns, and they actually often do not perform much better than the sentence-level models. Oh, yeah, oops, I forgot to change the animation, sorry. To kind of like look at the limitations of current context-aware models, for example, here the word it refers to report, which should be a masculine noun in French. So the pronoun should be the masculine il, but even the context-aware model incorrectly translates it to elle. And to try to find out why the model made this error, we can take a look at which tokens the model paid the most attention to, which we highlighted in yellow here. And we can see here that the model pays high attention to the word infirmary, which is actually a feminine noun when translated into French. However, it doesn't pay much attention to the antecedent, which is report or rapport. And this may explain why the model made this error. In general, context-aware machine translation models have been found to often attend to uninformative tokens in the context, such as the question mark here. or they do not use the information contained in the context at all. So in today's talk, I will be covering two of my works that tries to understand why existing context-aware machine translation models seem unable to use context adequately. And in the first work, we measured context usage in machine translation by calculating model agreement with human annotations. And then we tried to improve our model by supervising attention. And then in the second work, we performed a systematic analysis of what words require context during translation. And we developed a targeted benchmark to evaluate models on 5 types of ambiguous discourse phenomena that we identified. And you can also find the code and the data that support these 2 papers in the link shown here. So in the first part of this talk, I will present our work that tries to answer the question, do context-aware translation models pay the right attention? We therefore asked ourselves the following research questions. First, in context-aware translation, what context is useful to disambiguate hard translations, such as ambiguous pronouns or word senses? And 2, are context-aware machine translation models paying attention to the relevant context or not? And 3, if not, can we encourage them to do so? So first, we conducted a user study to collect the supporting context that human translators would use. We asked 20 professional English-French translators to select the correct translation and highlight the supporting context words that they used to answer. And we performed the study for 2 tasks. So first, pronoun anaphora resolution, where they choose the correct gendered French pronoun associated with a neutral English pronoun. And word sense disambiguation, where they choose the French translation of a polysemous English word. We gave translators varying amounts of the previous sentences in the English source side, as well as the French target side as context. And then we analyzed when translators were able to answer accurately and with high confidence, depending on how much context was given. We also analyzed the supporting context words that were selected by translators by looking at where these words are and whether it is an English or a French word, and features of the word, such as its part of speech and the syntactic dependencies. And you can check out our paper for the full analysis in detail. But yeah, to give a brief overview of our findings, for pronouns, the previous context sentences are useful, especially on the target side. And we also find that humans especially rely on the pronoun antecedent, or in other cases, the other reference of the pronoun in the target side. And we also found that the same co-reference chain we have in English is not as useful to translators because the chain in French carries information about the gender, whereas in English, it has no information about the gender. And for the word sense disambiguation, the current sentence in either language is often sufficient to disambiguate. So for example, charme in French means the quality of being charming, while porte-bonheur means a good luck charm. And we find that words that indicate the role or the meaning of the polysemous word are useful. Moreover, the source and target sides often contain an equal amount of semantic load used for word sense disambiguation, which is why either sides are as useful. And after our user study, we annotated the supporting context for 14,000 examples of pronoun anaphora resolution in English and French, and we released the SCAT dataset. Next, to evaluate whether models pay attention to the relevant context, we quantified how much model attention is aligned with SCAT. So for our experiments, we used a standard transformer translation model, but instead of only taking the data sentence by sentence, we incorporate the 5 previous source and target sentences as context by concatenating them to the current sentence that is then fed to the model. And we use 14 million parallel English-French sentences from the open subtitles dataset for training. So to quantify alignment between human and model attentions, we construct vectors that represent the SCAT annotations and model attentions when translating the ambiguous pronoun. And then we take the SCAT vector and the model attention vector. We first sort the tokens by decreasing model attention weights. Then we look for the rank of the first supporting context token from SCAT in the sorted vector. So in this example, the alignment score is 2. And the more attention the model assigns to the supporting context, the lower the alignment score. And we also used 2 additional alignment metrics, which you can find in our paper as well. So using this metric, we compare the alignment score of a uniform distribution with the alignment score of our model attention. And for the model attention, we measure alignment with SCAD for the encoder self-attention, the decoder cross-attention, and the decoder self-attention. We find that the alignment between the encoder self-attention and SCAD is slightly better than the alignment score of a uniform distribution. However, attentions in the decoder layers have very low alignment. And in general, context-aware translation models do not seem to pay attention to the relevant context. We therefore use SCAD to increase model human alignment. And to do so, we train a context-aware model on open subtitles with the standard negative log likelihood loss. And we additionally sample from SCAD during training, and we introduce the attention regularization loss. And we measure model performance using corpus level BLUE and COMET. However, words such as ambiguous pronouns usually represent only a small portion of all words in corpora. So corpus level metrics like BLUE and COMET may not clearly capture improvements in translating certain discourse phenomena. We therefore also compute the mean word F measure of translations of the ambiguous pronouns with respect to the reference pronouns. And we also perform contrastive evaluation, where we measure how often the model assigns a higher probability to the correct translation than the translation where the ambiguous pronoun is incorrect. And we find that attention regularization improves translation across all metrics, especially metrics that are targeted to pronouns. Therefore, regularizing attention with SCAD effectively improves ambiguous pronoun translation. And we also find better attention alignment with SCAD after attention regularization. We can also see that the model with attention regularization assigns high attention to the words report and hatba when we translate the ambiguous pronoun, and is then able to translate the pronoun correctly. So this suggests that attention regularization with SCAD can encourage models to pay the right attention and thus allowing them to translate ambiguous words correctly. And I didn't have too much time to go into all of the details. So our paper contains more experiments that demonstrate that the models with attention regularization rely more on supporting context selected by humans, and that regularizing the encoder self-attention gives the largest improvements in translation performance. And that performance on the word sense disambiguation does not improve when we only supervise the model attention using our annotations for pronoun resolution. So now in the second part of my talk, I will talk a little bit about how we can systematically identify words that require context to translate and how to evaluate context-aware machine translation models on them. And so we discussed how context is crucial to translate certain discourse phenomena, such as ambiguous pronouns, for example. However, while generating proper translations of these phenomena is important for our comprehension, they represent only a small portion of the words in natural language data. And because of this, common metrics such as BLUE do not provide a clear picture whether they are appropriately captured or not. And recent work tries to perform targeted evaluation using contrastive data sets like I described. But only a limited set of discourse phenomena for a few language pairs have been studied with this. And the difficulty of broadening these studies stems from the reliance of previous work for introspection and domain knowledge to identify what discourse phenomena is relevant. And then we also need to engineer language-specific methods to create these test suites or manually design these data for evaluation. And also, these evaluation methods tell us how accurately models can choose one translation over another, but this does not really measure translation performance directly. And so in this paper, we tried to fill this gap by proposing a data-driven, a semi-automatic methodology for first identifying the salient phenomena that requires context for translation. And then we applied this method to create a multilingual benchmark to test these discourse phenomena. And finally, we also evaluated different context-aware machine translation models on our benchmark. So in one of our previous papers that I can't go into too much detail today, we previously introduced a metric called CXMI. which measures context usage. And to give a quick overview of what it does, this is done by the context C and then measuring how much the information the context C can provide about the target Y given the source X. So basically how much the context is useful to predict the target Y. And so in this work, we asked ourselves if we can quantify on a more fine-grained level under which circumstances we require context. And we were interested in measuring how much the context is helpful for a particular sentence or particular words in a sentence. And so in this work, we proposed a sentence level extension of CXMI called point-wise cross-mutual information, which intuitively measures how much more or less likely a target sentence is when it is given the context or not. And we further extended this to the word level so that we can identify what kinds of words tend to see their likelihood increase when we give the context to the model. And to identify salient translation phenomena that require context, we performed a thematic analysis by examining words that had high PCXMI across different language pairs. And then we manually identified patterns and categorized them into phenomena. And so to give a brief step-by-step of the analysis we performed, first we examined the mean PCXMI per part of speech tag. And then we looked at the vocabulary items that had the high PCXMI to detect phenomena that are reflected by certain lexical items that consistently benefit from context. And finally, we looked at the individual tokens that had the highest PCXMI in the context of the sentence they are in, which allows us to identify patterns that do not depend on lexical features, but rather on syntactic constructions, for example. And we performed our analysis on data from TED transcripts as they have parallel document level data in several languages. We looked at 14 different language pairs, which we chose for the high availability of TED Talks, as well as for the diversity of language types in our comparative study. And in this table, we report the corpus level CXMI on the TED Talks data, as well as the mean of PCXMIs for the words in the data set. And first of all, we found relatively high PCXMI for proper nouns for several languages. And in this table, we show examples of words that had high PCXMI highlighted in pink, and then the related source of target words in blue and green. So in this example, context is helpful when proper nouns and the name entities may have multiple possible translations, but the same entity should be referred to by the same word in the translated document for lexical cohesion. So here, avilo is translated into Chinese as awei li'er, but for example, awei er is another plausible translation of the name. And we therefore need context to know which translation has been adopted in the document and to translate this consistently. And next, we found high PCXMI for second-person pronouns in languages where they encode politeness distinction, such as German, Spanish, French, etc. And while English uses the same second-person pronouns for everyone, some languages perform TV distinction, where the pronoun depends on the level of formality and the relationship between the speaker and the addressee. So in this example, in French, we say votre for your if you want to show respect to the person we're speaking to, such as an older stranger or our boss. But for more casual conversations, such as to a friend, ta would be used here instead. So we need the contextual information on the relationship between the two speakers. And furthermore, for languages like Japanese and Korean, where we have honorifics and speech levels for politeness distinction, we find high PCXMI on verbs and particles. And so in these languages, prefixes and suffixes of certain words and the verb lemma depend on the relationship between the speakers and the formality of the discourse. So for example, in this example, the verb hosoku shita, the particle that indicates a casual politeness level in Japanese, but in a more formal conversation, we would instead say hosoku shimashita, for example. And we find that several languages have high PCXMI on pronouns. And these are usually languages that use gendered pronouns that are not used in English. Or another example is dual pronouns in Arabic, where in Arabic, they make the distinction between singular, dual, and plural pronouns. So to give an example of that, so shovel and picks are grammatically feminine in Portuguese. So the pronouns to refer to them should be the plural feminine noun, elas instead of eles. However, English does not have grammatical gender assignments and do not use the gendered third person plural pronouns either. So we need context to understand what they refers to and which gender to use. And we also find high-speed XMI for certain verb forms, such as the future form in Italian or the imperfect form in Spanish and French. And while English verbs may have up to 5 forms, other languages often have a more fine-grained system for verb forms. For example, English has only a single form for the past tense, whereas languages like Spanish and French have multiple verb forms for the past tense alone. And in this example, the verb tenía for had and hacían for made are in the imperfect form because the context of these sentences is used to describe actions that have no definite beginning or end. However, if these verbs were used to describe a single event rather than a continuous event, then the preterite form would be used instead. So verbs must be translated using the verb form that can reflect the tone, the mood, and the cohesion of the document. And finally, among individual tokens that have the highest PCXMI, we find that many are due to ellipsis in the English sentence that does not occur on the target side. For example, here the English text does not repeat the verb no in the second sentence because it can be understood from the previous sentence. However, in Turkish, there's no natural way to translate the verb phrase ellipsis, and so we must infer that don't refers to don't know and translate the verb accordingly. So for the interest of time, I won't go into the details of each tagger, but basically we created methods to automatically tag words for the 5 discourse phenomena we just described. And to verify the correctness of our automatic tagger, we asked native speakers of 9 languages we studied to manually verify the Muda tags that we obtained on randomly selected utterances. And across all languages that we evaluated, we achieved high precision on all the tags except for ellipsis. And so improvements for the ellipsis tagger is still an ongoing work. So to summarize, we evaluated a sentence level, this wasn't the conclusion yet. Last section. So we evaluated a sentence level machine translation model and a context empty model on our system to see how they would do on our benchmark. And in this big table, we show the results of our base models that were trained either without context or with context. And basically, we find that although blue scores are highest for models with context gold for most language pairs, Comet is more often higher for the no context models. And in terms of mean word F measure for all the words, we do not really find significant differences between the 3 systems we compared. And so it is therefore difficult to see which system performs the best when we only use these corpus level metrics. And for words that do require context for translation that are tagged with Muda, our context-aware models obtain only marginally higher word F measure than the context-agnostic models, which suggests that these models are not sensitive enough to context or they are unable to use the relevant information from context to translate the ambiguous words at all. And we also tried evaluating stronger models that were pre-trained on a large corpora for German, French, Japanese, and Chinese. And for these pre-trained large models, context-aware models obtain slightly higher scores on corpus level metrics. And we do find that improvements are more pronounced for certain tags, such as ellipsis, lexical cohesion, and formality. And finally, we also looked at commercially available machine translation engines to see whether they can leverage context and perform well on the Muda benchmark. So the first engine we looked at was Google Translate, which from our experiments is actually only sentence level. And then the DeepL translator that advertises the usage of context as part of their translations. And among commercial engines, DeepL seems to outperform Google Translate on most metrics and language pairs. And also the sentence level ablation of DeepL, where we made it perform sentence level translation, performs worse than the document level system for most Muda tags, which further suggests that DeepL is able to handle context to some extent. But overall, curative MT models are unable to obtain considerable improvements over their context-agnostic counterparts on our challenging Buddha benchmark. And so we encourage the development of models that can address the ambiguities of Buddha. So this is the end of my talk. Sorry that I ran a little bit over the allocated time, but I'm happy to take questions now.
Thanks, it's perfect timing. So thanks for your talk. It's really very inspiring. So any questions from the audience? You can just pop up or just write your questions in the chat.
Hi, it's Bill from the University of Edinburgh, and I think I have a question regarding your first work. Firstly, it's a great talk and a very nice work. So in your first study, I think you used you analyzed some context usage based on the attention. So I'm wondering how you perform that analysis and to what extent can we trust attention scores? Because there are a lot of debate whether attention is interpretable or not. So and how you think about this?
Yeah, that's a very good point that attention maps don't necessarily have this guarantee of causality. So it's still debatable whether the attention mechanism is a black box in itself. And that's also something that I am very much aware of and I'm trying to keep in mind. So for us, we basically wanted to use attention because of the second step where it's easier to supervise attention and to kind of edit the model mechanism and then force the model to pay attention to certain words or not. Whereas if we use saliency maps, for example, for the study, then it would have been harder to manipulate that. And I think you had one question on how we actually interpreted attention. So that was just taking the attention heads and then looking at the mean of how much attention that model assigned to for every word in either the source input or the target input. And so from there, we kind of obtained our model saliency scores using the attention maps. And then we had several alignment metrics that can compare the saliency maps obtained from the model with some saliency maps that were human generated. So these are basically binary maps where the humans annotators were asked to select in the context whether the word is useful or not useful for the certain context-aware translation that we gave it. I hope this answers your question. Feel free to follow up if you have any other.
Oh, great, thanks.
So we have a question from the chat. Okay, or
no, just go ahead with the one from the chat. I can wait.
Sorry. Yeah. So Valentini has a question. So when you found that there were errors in the pronouns, did you notice whether there was a tendency of use of a masculine or it would always align with the gender of the word of the system through was a matching context?
Yeah, this is a great question. So what I found, at least from qualitative analysis, was that when there was no salient context that would give the model some other information, then yes, the model would kind of by default translate neutral pronouns into the masculine pronouns in the target language. But then in some of the examples that I've shown before, I don't know if I can go back, there's a lot of slides. If there was a certain word that the model did pay high attention to, which was of the feminine gender, even though the model was supposed to generate the masculine pronoun. So this is one example. Then the model would generate the female pronoun because it kind of overly relied on some spurious female noun that was apparent in the sentence that it was given. So my answer is that by default, it does have a bias or tendency to generate masculine pronouns, but this bias is kind of overridden when there's a stronger signal for a model that thinks that there's a dependency with a female pronoun.
Thanks for your answers.
Thank you.
Yeah. Okay, so yeah, Christian.
Yeah, thank you very much for your really cool talk.
Thank you.
I have a question that's I'm not sure you will be able to answer because it's not it goes a bit beyond what you presented here, because I think you said that for the word sense disambiguation you found that local context was often enough. Did I understand that correctly?
Yes, so that was so like the caveat here is that local context was enough for the set of data that we had that we could use to evaluate. So that's like a slight caveat, and like there could be data with other examples of word sense disambiguation where that could not be the case.
Yeah, because what you said seems to be a bit at odds with what we heard earlier today in Shayla's talk on machine translation evaluation, where she actually found, if I understood her correctly, that lexical ambiguities often require very extensive context to disambiguate. And I'm just wondering, I mean, I think there must be some difference in what you're measuring here, clearly, because both of you are measuring something which is superficially similar, but you're coming to different conclusions. So where is the difference here? And I mean, I realize that you're probably not too familiar with Shayla's work, but I'm just curious if anything can be
I
said about
unfortunately
that.
missed the other talk, but I'd be very interested now in looking at the other conclusion. But I think it's definitely possible, like we have like opposing conclusions that are both correct. And my best guess is really that it's the nature of the data that we both used, because I think word sense disambiguation, I have a example here. Like there are examples where you would need like longer range context in order to know it, but like at least in this test set that I had, like usually it's kind of obvious in the current sentence, either from like the semantic knowledge that we have in the current sentence. So here, like it's Ace of Diamonds, which we can kind of infer that it's about playing cards and it's not about the gemstones. So there we don't really need any context beyond that. So yeah, my guess is that maybe the other work has focused more on word sense disambiguation that isn't as local as the ones that I evaluated my translations on. Yeah.
Yeah. Thank you very much.
Yeah. Thanks.